What's up, everybody, and welcome back to another video on the Digital SAT from the Scalar Learning channel. Today, we are talking about my predictions for what to expect on the math section of the October Digital SAT. Without further ado, let's do it. And one quick note, if you are looking for the best resource for practice materials for the Digital SAT, I highly recommend the SAT Crash Course. You can see the discount code above. Use the code SCALAR for 20% off. So one of the trends that I've been seeing with some of the practice materials is that we're now having these modified functions, right? Where they're throwing in these little constants. Now, this is a linear equation word problem. And the reason why I think this constant is significant, this D value, is because it's making it so that you can't just simply plug and chug into decimals, right? There's a little bit more to it. Now, on top of that, they're saying, hey, what is the x-intercept of f of x plus 9, right? So in order to do a problem like this, okay, what you're going to start with is plugging in that plus 9, right? Because they want the x-intercept of f of x plus 9. Now, there is still a workaround to use Desmos, and I'm going to show you that in a second. But to me, the best way to solve this is to go in and solve it by hand. Now, I think there's going to be a lot of instances on this test where you might just instantly be like, all right, I'm going to go to Desmos, I'm going to plug this in. But I want to caution against that. And again, I think that's part of the intent of the test makers is to make the test less solvable by a straight plug and chug into Desmos. Of course, you can still use Desmos. You might have to do so in a more intelligent, in a more thoughtful way. But anyways, as we simplify this, we get 6d times 20x plus 21 plus 17 plus 9, which is 26. Now, we're trying to find the x-intercept, right, of any function. We're talking about where it hits the x-axis. And at that point, the function value is 0. So now as we actually try to solve for the x-intercept, what we're doing is we're really solving for this x value, meaning we're isolating x. So now let's do that. Now we're going to subtract by 26, right? We got negative 26 equals 6d times 20x plus 21. Then I'm going to divide both sides by 6d like so. Those are going to cancel out, and then we're left with 20x plus 21. Then I'm going to minus 21. So now we got negative 26 over 6d minus 21 equals 20x. Last but not least, I'm going to divide both sides by 20. So we get 21 over 20. But when I divide this by 20, it's like multiplying the denominator by 20. So now what we're going to have, and I'm going to switch around the order here, we're going to have negative 21 over 20 minus 26 over 6 times 20, which is 120d. And again, this is my x value. Now, here's the dealio, right? This doesn't actually line up with anything we're seeing here, but I am seeing some kind of similar options, right? With that negative 26 over 120d. Well, if I make this have a common denominator, right? I multiply the top and bottom by 6d. Now I get negative 126d minus 26 over that nice common denominator of 120d, which means that A would be the winner. That's how you do it. Done. Now, if we were to use Desmos, you see I wrote the function in here like so. I set an arbitrary value for d. Now, the only thing I want to caution you against is setting the constant to either 1 or 0. I usually try and avoid that, but here I set it to 2, and now we're going to test out our answer choices. So I'm going to go straight to the answer choice that we know is correct, and I'm going to write that in as a coordinate verbatim. So I put in option A just like it was written on the actual test, and you see it's using that same constant, that same value of d, which is 2, and when you plug it in and put it in coordinate format just like this, look at that. It shows up right in the correct position. So you can see this is indeed the correct x-intercept, double verified, done. Now, this one is another twist on a very typical type of problem. This is a system of equations. And, normally you can just plug this right in to Desmos and solve for the intersection point. But here's the deal. They've modified this with this crazy little constant. It says for each real number r, which of the following points lies on the graph of the equation in the xy plane of the given system. So this one's a little twist, right? Now, the other thing that you're going to notice in this equation, this is a very difficult problem, is that both of these equations are actually the same. If I multiply the top by 5, right, I actually get the exact same as the second equation. I get 10x plus 15y equals 35. So what that means is that these two lines overlap, meaning there's infinite solutions. Now that we know that this is the case, that we're only dealing with really one equation, I'll put it in its most simplest form, which is 2x plus 3y is equal to 7. What we're dealing with here is essentially our relationship between x and y. Notice in B, right, we're plugging in r for y and then we're getting a corresponding value of x. For C and D, we're plugging in R for x, and we're getting a corresponding value for y. The odd man out is A, but we're going to deal with that later. Maybe it's correct, maybe it's not, but let's first start with B, C, and D. So what I'm going to do is I'm going to plug R in for y, then I'm going to isolate x and see what we get. So here we go, 2x plus 3r equals 7, 2x equals 7 minus 3r, divide both sides by 2, and x equals 7 halves minus 3 over 2r. So when I look at this equation, look at that. I get that exactly. If y is r, my x is negative 3 halves r plus 7 halves, which means we just confirmed that B is the winner. Now, just for fun, let's actually see what C and D give us. I'm going to plug r in for x, and now that I've done that, we're going to isolate y and see what we get for y. So 3y equals 7 minus 2r divided by 3. Y is equal to 7/3 minus 2/3 r. Now this one's close, 7/3 plus 2/3 r, but that's not exactly right. And this one's totally different, 7 halves and then a negative 3r over 2. Now the way we can verify this in Desmos is we can take our linear equation, our line, and we can plug in the option that we think is correct with a constant for r, move that around and see if that always stays on this line. So let's check that out. So here's the point that we believe to be correct. And again, r can be anything, right? So I got to move the constant r and it should always stay in the line. And look at that, it's right on the money. So what you could have done as well is gone straight to Desmos and run through each option. But this is another case where I actually feel like doing it by hand might have been a little bit faster. So there you go, 2 ways to do it, boom, done. Next, we're on to another system of linear equation word problem, but this is in particular a mixture problem, and I do anticipate that you're going to see a mixture problem like this. So let me show you how to set this up and solve. So it says a sample of a certain alloy has a total mass of 50 and is 50% silicon by mass. The sample was created by combining 2 pieces of different alloys. The first piece was 30% silicon by mass, and the second piece was 80% silicon by mass. What was the mass in grams of the silicon in the second piece? So we're going to come back to what that's getting to in a second. But here's the dealio, right? I need a representation of the total mass of the 30% alloy, which I'll call X, and of the total mass of the 80% alloy, I'm going to call that Y. Now we can make a great equation. So we can say 30% of my total quantity of X, which is actually giving me the silicon in X, right? Plus 80% of Y, and the two combined are going to give me this nice alloy that is a total mass of 50 grams at 50% silicon, right? And so you notice we have kind of a similarity on both the left and right hand side. We have a percentage times a total equals a percentage times a total, okay? Now, the second thing that we know is since the final mass is 50 and these are the masses of the two alloys at the beginning, we know that X plus Y, therefore, is also equal to 50. So what is this? This is a system of equations, right? Now that we've kind of put everything together, it's a nice system. Now we can solve. So I'm going to multiply 0.5 times 50. That's 25. Let's rewrite the equations up here. So now I'm going to put the second equation up here, but I'm going to set it up for elimination by multiplying the bottom equation by negative 0.3. So I have negative 0.3x minus 0.3y is equal to, and then 0.3 times 50, you can of course use a calculator, but it's negative 15, right? 3 times 50 is 150, 0.3 times 50 is 15. Now we're going to add these two together. These are going to cancel out. 0.8y minus 0.3y is 0.5y, and then 25 minus 15 or plus negative 15 is 10. Last but not least, we're going to divide by half, and we get y. Dividing by 0.5 is like multiplying by 2. 10 times 2 is 20. So that's the mass of y. So you might think, hey, there's my answer. I'm done. I'm out. No worries. But that's really not what they're asking. They're saying, what is the mass of the silicon in the second piece? So the total mass of the second piece is 20, but the mass of the silicon, well, it's 80% silicon. So I have to take 80% of 20, and that is 16. So this is a particularly difficult mixture problem, in my opinion. That's how you set it up. That's how you do it. Done. The next type of question that I'm anticipating is a percentage problem, and they can come in kind of two different flavors, right? So we can talk about taking a percent of something, and we can also talk about taking percent greater than whatever, right? So or a percent increase, something like that. So let's look at this example. And the way that I want to attack this is by turning it straight up into an equation. So for example, my is word is really important because that's an equal sign. So we say 210 is, now it's not saying, so it said, if it said p percent of 30, 210 is p percent of 30. I'd just be like, cool, p percent of 30, and there'd be my equation. But it doesn't say that. It says greater, okay? So you have to think about what that means. Oh, it's p% greater than 30. So we're taking p% of 30 and then we're adding 30 to it like so. So that's what greater than or an increase means, right? If you ever get tripped up in terms of trying to understand that language, think about if you said like, hey, I have $200. What's 50% greater than $200? Oh, it's not, you wouldn't take 50% of it and say I have $100. You take 50% and add it onto the original and say I have 300. Now we can solve, we'd minus 30 from both sides. 180 equals p over 100 times 30. Then we divide both sides by 30. 6 equals p over 100. Last step, multiply both sides by 100, and p is equal to 600. So this represents 600%. 600 is the winner. Done. The next type of problem that I'm anticipating is a density problem. I've been seeing these problems show up more and more on the practice materials. And the interesting thing is they don't actually give you the formula for density in most of these questions. So I do believe it's important to know the formula for density. Density is equal to mass divided by volume. So let's step through this problem and let's see how we take care of it. So it says an object has a mass of 168 grams and a volume of 24 cubic centimeters. What is the density? So again, if you know the formula, it's pretty straightforward. 24 goes into 168 7 times. A is the winner, but I do think it's very important that you have this formula down. It's not too complicated, so make sure to review it right before the test. That's how you do it. Done. Another question that I'm anticipating is a standard deviation question. These used to show up a lot on the old version of the SAT, and I feel like they're going to show up this October. They're going to show up on Saturday. So let's take a look at how to approach a standard deviation problem. Now, the beautiful thing about standard deviation problems on the SAT is you don't actually have to remember how to calculate standard deviation. You have to understand what standard deviation is, though, which is simply the spread of the data. The more spread out it is from the center, the greater the standard deviation. The more tightly packed it is, the more closer it is to the mean, to the center, the smaller the standard deviation is. So when I look at this data, it looks pretty similar, but this one looks more spread out, right? So I would say the standard deviation of B, without even doing any calculations, is greater, right, than A. So here it says the standard deviation of A is equal to the standard deviation of B. I disagree with that. I would say 2 is not true, which means this is out and this is out. By the way, this question is also asking about the median. We can assess the median. The median is always the middle value. In dataset A, we have 17 values, and same with dataset B, which means they have an exact middle, an exact median. And the middle value for this one is 13. The middle value for this one is also going to be 13, right? Which means that the medians are indeed equal. Therefore, 1 is true, not 2. That's how you do it. Done. Another type of problem that I'm anticipating is a length to area conversion, okay? And these can be really sneaky because you get this area, right? You say, oh, it's 4.36 square miles. And it's like, oh, if I want to convert it to yards, they're telling me the conversion. If this is, miles squared, 1 mile is 1760 yards. So I just take 4.36 and I multiply it by 1760, okay? And the messed up thing is they have a value if you carry out that operation, which is option B. But B is not the right answer, okay? And I'm going to explain it as follows. So think about it like this. Let's say you have 1 square mile, meaning it's 1 mile by 1 mile. Okay, so you'd be like, all right, well, so if 1 mile is equal to 1,760 yards, then is 1 square mile equal to 1,760 square yards? You might be like, yeah, that seems logical. But think again, because think about it. 1 mile would really be 1,760 yards by another mile, which is another 1,760 yards. And now to get the area, you multiply these two together. So it'd be way bigger than 1,760. It'd be 1,760 squared. So as a shortcut, if you're ever trying to convert between square units and they give you the conversion for just the straight up length measurement, what you do is this. You say, all right, so 1 mile equals 1,760 yards. 1 mile squared and 1,760, yards squared. What I do, I square the values as well. I square 1 and I square 1,760. And now I have an equivalency for area. If I had to go to volume, I take the same thing and I cube it, right? I cube both those values. But anyways, now we have our equivalency for area. So now what do is I take my 4.36 and I multiply it by 1,760 squared. And there we get 13,505,536. So we of course know that D is the answer, but I want to show you one other way to approach it. Some people might like this better. It's a bit more conceptual and a bit easier to wrap your head around. So again, we have 4.36 square miles. Well, what if I did this? Okay, what if I made a little fake rectangular plot that has that exact same area, meaning it'd be 1 mile by 4.36 miles, right? That gives me an area of 4.36 square miles when I multiply them together. Then I can individually convert these to yards, right? So then you don't have to worry like, hey, what was that conversion again? Do I square it? Do I cube it? Whatever. So be like, oh, cool. This is 1,760 yards. And then convert this one by just multiplying 4.36 times 1,760, which is 7,673.6. And then to get the final area in yards squared, right? I take these two values and I multiply them, right? Length times width. So this value times 1,760, and we come back to that same answer. So therefore, D is the winner. Done. Another type of problem that I've been seeing on some of the practice materials recently released from the College Board are these mean proportional right triangles. So what is a mean proportional right triangle? It's when we have a right triangle and then we drop an altitude, creating two other right triangles. But the important thing is these other two right triangles are actually proportionate or similar to the original triangle, meaning we've now created three similar right triangles. So the way we can use that information to solve something like this will be as follows, right? So let's mark in everything that we're given. We know that AD is 121 over 3. We know that AB is 11 rad 130 over 3. So now they're asking for the length of DC. So there's a couple of ways that we can approach this, but the first thing I see is for this triangle right here, we have one of the legs and we have the hypotenuse. So right off the bat, I can use Pythagorean's theorem to solve for this side. And this side here, BD, which is also the altitude of the big dog, right? That usually is a very important side because it's simultaneously in this triangle and in this triangle as well. So what I did here is I just plugged in Pythagorean's theorem right into Desmos, and this is going to output a nice value for x. Obviously, we have a negative and a positive, but since this is a side length, we're only taking the positive value. So there we go. We got our side as 11. So now I can fill this in for BD as 11, but we're not trying to solve for BD. We're trying to get DC. But here's the beauty of finding this side length. We can now, since we know that these are all proportionate triangles, set up a really nice proportion. So let me show you how I'm going to do that. This is the little leg of this triangle. This is the big leg, and this is the hypotenuse. 11 for the medium-sized triangle is the little leg. This one is the big leg, and this is the hypotenuse. So what I can do is I can set up a little leg to big leg proportion. So again, for this triangle, I can say little leg, which is 11, over big leg, which is 121 over 3, equals, and then we're going to go to the smaller triangle. We're going to say little leg on top, which is my unknown, which is what we're solving for, over the medium leg of the small triangle, which is BD, right? And now we have this beautiful proportion, and now we can cross multiply and solve for x. So x times that is 121 over 3x equals 11 times 11 is 121. To isolate, we're going to multiply by the reciprocal of this, which is 3 over 121. So it's 121 times 3 over 121. Cancel, cancel, and we get x is equal to 3, which is the length of DC. So 3 is the winner. Done. Finally, we've got this crazy little polynomial, and I did talk about this one in my August prediction, but again, I think this is a great one that we can expect to see because not only is it a polynomial function that also goes to like factors of a function and finding your nice roots, you know, things that are going to zero out the function, but it also has got a little bit of quadratic stuff in the mix too, and I'm going to show you how that factors in. So here they're saying the sum of the solutions of this equation is 20 over 3. What is the value of p? So since everything is factored and set equal to 0, we just got to find what values of x zero this piece out, and this piece out individually and add them all up. Okay, so what is going to zero this out? Well, we're trying to figure out when is 3x plus p going to equal 0. Now I can just isolate x. 3x equals negative p. X equals negative p over 3, right? So that is the solution for this first part. What about for this part? Well, to simplify it, I can factor out a 5, and I can say that's x squared minus 9 left inside. Then I can factor that, right? It's a difference of squares, x minus 3, x plus 3. That means my two solutions there are plus or minus 3, right? 3 here will zero this out, negative 3 here will zero this out, etc. So those are my two solutions, positive and negative 3. Okay, and last but not least, we got this guy. Okay, so you might say, all right, well, maybe we can factor it, but then we got a p in there. Maybe we can use quadratic formula and find the solutions that way, but there's a little shortcut, right? That's why this is such a hard but very interesting problem, because to find the solutions of this, well, this is a quadratic, and I'm looking at that in isolation. I can ignore this. And so since we're adding all the solutions together anyways, if you remember, one of those super important formulas for sum of solutions for a quadratic is negative b over a. Not negative b over 2a, that's the x value of the vertex, but negative b over a. So that's a, that's b, that's c. Negative b would be positive 16 over a, which is 2, meaning the sum of the solutions right here is going to be 8. I don't care what each of them individually are because I'm adding them up anyway, so we're adding 8 on over here. And then it's saying all of this is equal to 20 over 3. Now we got this amazing equation with p in the mix, and now we solve. 3 minus 3 is 0. Then I'm going to minus 8 from both sides, right, and kill that. Now, obviously, to simplify, I'd love to have common denominators, so I'm going to multiply by 3 over 3. Then I have 20 thirds minus 24 thirds. And 20 minus 24 is, of course, negative 4. So I have negative 4 thirds equals negative p over 3. Multiply both sides by negative 1. Boom, boom. And so if p over 3 equals 4 over 3, p must equal 4, which means 4 is the winner. That's how you do it. Done. I hope you guys enjoyed this video, and if you did, please click that like button. If you want to see more videos from the Scalar Learning channel, make sure to click subscribe. But just remember, for all these predictions, everything I'm going over, I want to make sure that you have everything down packed. If you don't, make sure to check out our Formula Bible. And if you're looking at critical concepts right before the test, make sure to check out our SAT Critical Concept Bible as well. That's a 2-hour plus video. Thank you guys so much for joining, and I wish you all the best of luck on test day. Take it easy.